So today we will cover three topics, if time permits: ensembles and beta parameter, and then relation between entropy and probability. So let us start with the first topic, which is ensembles. So put the heading ensembles. So till now we have studied the system. And system means it is the collection of identical particles in large number, or we can say that system is a collection of large number of identical particles. Now we have to study the ensemble. An ensemble means it is collection of large number of systems, such that these systems are macroscopically same and non-interacting. So system is a collection of a large number of the identical particles, and then ensemble is a collection of large number of systems, such that these systems are macroscopically same and non-interacting. So what is the meaning of macroscopically? Means the macroscopic properties will be same. Macroscopic properties of the system will be same. And these macroscopic properties are like the volume, then energy, pressure, temperature, then number of particles. So these properties like volume, energy, pressure, temperature and number of particles, these properties are the macroscopic properties, and these properties will remain same for all the system inside the ensemble, but microscopically they will be different. So now the ensembles are of three varieties. Ensembles are of three types. And these three types are macrocanonical, microcanonical, then canonical, and grand canonical. So we have three types of the ensembles: microcanonical, canonical and grand canonical ensembles. And then we take one by one all these three ensembles. So let us go to new page and put the heading microcanonical ensemble. Put the heading Microcanonical ensemble. Microcanonical ensemble. So in this system, in microcanonical system ensemble, all the systems have same energy, volume and number of particles. So all the systems have same energy, volume and the number of particles. Now we can draw the system as, let us draw few boxes. So I will draw 9 boxes like this. So these boxes represents each system. One box means one system. One system. And all the system have same energy, volume and number of particles. So I will write EVN. In each box I will write EVN. Means all these systems have energy E, volume V and number of particles N. Number of particles N. So write EVN in each box. EVN. EVN. And these are the systems. Then draw another boundary covering all these systems to show that these systems are a part of ensemble. These systems are part of ensemble. So let us cover all these systems into ensemble. Then we can draw different lines here. And draw various lines here also in between these. That is shaded portion. So these shaded portions show that there is insulation between all the system. These shaded portions show that there is insulation between all the system. Now since in microcanonical ensemble EVN are constant, so how we will maintain this condition that E is constant? E is constant. It means that the wall of the system should be insulated, thermally insulated. The wall of the system should be thermally insulated, and therefore no heat can be transferred from one system to another system, and energy will remain constant in each the system. Then we have the condition that volume is constant. So how we will maintain this condition that volume is constant? The wall should be rigid. The wall should be rigid. It means that we cannot compress the wall or we cannot expand the wall. So the volume will remain constant. And then the third condition is that N is constant. Number of particles in the system is constant. So for this the wall should be impermeable. Impermeable wall. Impermeable wall means the particles cannot go from one system to another system. And so these three conditions on the wall will define the microcanonical ensemble. Now come to the another system, which is the canonical ensemble. So come to another system, canonical ensemble. Canonical ensemble. So in canonical ensemble, we have TVN constant. T means temperature, volume and the number of particles. These three quantities are constant. So now I will make another diagram to represent the canonical ensemble, and this diagram will be different. Again there will be 9 systems. So now I will join all the system with a solid line because there is no thermal insulation. So all these systems are joined by a solid line, and here let us write TVN. In each system write TVN. TVN. Temperature, volume and number of particles. These are constant in the each system. TVN, and then cover this whole system to show that these systems are part of one ensemble. One ensemble. And now we have conditions that temperature is constant. Temperature is constant. So if the temperature is constant, it means now the wall is conducting wall. This wall is conducting wall. It is not the insulated wall. Therefore, in this figure, which is the microcanonical, these lines show that all the systems are insulated from each other, but now all the systems are not insulated, but they are thermally connected. Therefore, the energy or heat can transfer from one system to another system such that now the temperature is constant for all. So, in the macrocanonical, it is the energy which is constant, but now in the canonical, it is the temperature which is constant. So, wall is conducting, and then we have again the same condition that volume is constant. So, volume is constant means the wall is rigid wall. It is a rigid wall. Therefore, we cannot compress and expand the wall, and the volume will remain constant. Then again the same condition that number of particles is constant. So number of particle is constant means the wall is again, it is impermeable. It is impermeable. Therefore, the particles cannot move through the wall of the system. So this represents the canonical ensemble. Now go to the next page and put the heading Grand Canonical Ensemble. Put the heading Grand Canonical Ensemble. In Grand Canonical Ensemble, now it is mu, v and t, or you can write in the previous style. So it is T, V and mu. So these three quantities are constant. T means temperature, V is the volume and mu is the chemical potential. Mu is the chemical potential. Chemical potential. This is mu, and this is the gradient of the concentration. Gradient of concentration of particles. Concentration of particles. So now let us make another system, and in this system now we will have a similar picture as it was in the canonical, but there will be some difference. So put this boundary, and now we will draw the dashed lines. Draw the dashed line. This dashed line has some meaning. Put the dashed line here, not the solid line. It is the dashed line. And then enclose this system, these systems into the ensemble. So draw outer boundary. This is the outer boundary. And in each box is representing a system. We will write TV mu. TV mu. TV mu. T means temperature, V means volume, and mu means the chemical potential. TV mu. So now what should be the condition for the wall? Since temperature is constant, therefore wall should be, wall means wall of the system, this wall should be conducting, it should be conducting. And then the next condition is volume is constant. It means again that wall is rigid wall, it is a rigid wall. And then now we have different condition that mu is constant. Mu is the chemical potential, means the gradient of the concentration. So to maintain the condition that mu is constant, if there is some gradient in the concentration, means the number of particles in one system is more than the number of particles in the other system, then they can flow from one system to another system such that the concentration will become equal in each the system. And therefore now this wall should be permeable. This wall should be permeable. Permeable wall. Permeable wall. And therefore I have shown these walls by the dotted line, means the particles can go from one system to another system and the flow will be maintained up to that time when the concentration become equal in all the system, and in such case the mu will be constant, but the number of particles will not the constant, but the mu will remain constant in each system. So this is the canonical and grand canonical ensemble. Now the next is the ensemble average. Ensemble average. Because we have many systems in one ensemble, therefore if the property ui is different in each system, we can calculate the ensemble average of ui. One can calculate ensemble average of ui. So how we can calculate? So ui is the property a function showing the property, and suppose the ith system, ith type of the system which have this property ui has number ni, means ni systems will have the property ui. You can write it in a different way. Let us write it: ni systems have property ui. So what will be the ensemble average? Ensemble average u bar. We will write it as u bar. U bar means the average value of this property. U bar is equal to n1 u1 plus n2 u2 plus n3 u3 and so on and so on, and then this divided by the total number of the system, which is n1 plus n2 plus n3 plus n4 and so on. So in short, we can write it as summation over I ni ui divided by summation over I ni. So this average is the same thing. If we take for more clarity, let me give one example to you. Suppose in a class of 60 students, in a class of 60 students, for 5 students have, suppose 5 students have the weight 45 kg, and 7 has the weight 50 kg, and then 9 have the weight 52, and then 20 have the weight 57, and then 14 have the weight 60, and then 5 students have weight 65 kg. So this total number is 60. So how we will calculate the average weight? Average weight of the class, that is 5 into 45 plus 7 into 50 plus 9 into 52 plus 20 into 57 plus 14 into 60 plus 5 into 65, and all this divided by the total number. So total number means 5 plus 7 plus 9 plus 20 plus 14 plus 5, that is 60, divided by 60. So this is the normal way of taking the average, and the same way is represented by this formula also, that ensemble average of any property U can be taken like this, where U1 means the N1 systems have the property U1, N2 systems have the property U2, and so on. So this is known as the ensemble average. Now we have the properties of ensemble average. So go to a next page and put the heading properties. Properties of ensemble average. Ensemble average. So here we have 3 properties. The first property is that ensemble average of the sum and difference or difference of the two functions will be the sum and difference of the ensemble average of two functions. So I am writing in short, but you have to write the full sentence. I am writing in short. Ensemble average of sum or difference of two functions is equal to sum or difference of ensemble average of two functions. So when I will write the mathematical equation, then it will become more clear. It means that if there are two functions f and g, then the sum or difference of the two function and the ensemble average of the sum or difference of the two function is equal to sum or difference of the ensemble average of the two. So what is the difference here? First I have taken the sum or difference, then taken the ensemble average, and here it is the ensemble average of the function plus minus ensemble average of the other functions. So this is the mathematical equation denoting the property. Now the second property is that ensemble average of the product of constant and a function is equal to constant multiplied by the ensemble average of the function. So let us write it here. Ensemble average of product of constant and a function is equal to product of constant and ensemble average of function. So mathematically we can express it like this: some constant c, product of some constant c and the function f. So ensemble average of the product of constant and the function is equal to constant and then the ensemble average of the function. So this is the second property. Now come to the third property. Third property is that ensemble average of the product of two functions. Ensemble average of the product of two functions is equal to product of the ensemble average of the both function. So let us write it here. Ensemble average of product of two functions is equal to product of ensemble average of two functions. So mathematically we can express it like this: two functions f, product of two functions, then ensemble average. So ensemble average of the product of two functions is equal to the product of the ensemble average of the two functions. So these are the properties of the ensemble average. So this is all about the ensembles. Now go to the next page, and before going into next page, if you have any query about this topic, then you can ask. If you have any doubt or any query about this topic, very straightforward topic and very interesting topic. So go to the next page, and the next topic is the beta parameter. So write down the condition of equilibrium, the condition of equilibrium, between two systems in thermal contact, between two systems in thermal contact. That is beta parameter. Means that if the two systems are in thermal contact with each other, then what will be the condition of the equilibrium? So let us define a system. So this is a system, and then I have divided this system into the two parts. So the first part is A and the part is B, and the first part has the volume VA and the part has the volume VB. Then first part has the energy E and another part has the energy E dash. So these are the two systems, and these two systems are in thermal contact with each other, and because they have the different energy E and E dash, therefore they can transfer the heat from one side to another side because they are in the thermal contact. So the first condition is that the E plus E dash is equal to constant, which is equal to the total energy of the system. So the total energy of the combined system or the composite system is E dash. So E plus E dash is equal to E star. Now let us differentiate it. Then on differentiating, we have day by E plus day by E dash will be, what will be the day by E star? Anyone? Switch on your mic and tell me what will be the day by E star. Differentiation of E star, where E star is the total energy which is constant.
0.
Yes, it is 0. So that because the total energy is constant, therefore the differentiation will be 0. Good. Now, if day by E plus day by E dash is equal to 0, it means that day by E dash is equal to minus day by E, and this also shows that day by E dash upon day by E is equal to minus 1. So this is one condition which we have, day by E dash upon day by E is equal to minus 1, and we will use this condition afterward. Now the probability that the system has energy E. So this probability is some constant C multiplied by the thermodynamic probability. What is the thermodynamic probability? This thermodynamic probability omega, which is the thermodynamic probability. Let us recall this word which we have discussed in the previous lecture. Thermodynamic probability. This is equal to number of microstates. Number of microstates corresponding to given macro state, and we have derived the condition that if there are total n number of particles, capital N particles, and they are distributed into n1, n2, n3 cells, then this omega or the number of microstates is given by the formula n factorial divided by n1 factorial, n2 factorial, n3 factorial, and so on. So this is the formula for the thermodynamic probability. So now come to this thermodynamic probability. So the probability for the system having energy E is equal to some constant C multiplied by the thermodynamic probability. In a similar way, the probability of the another system having the energy E dash is equal to some constant C dash into omega E dash. So what will be the composite probability of the whole system? Composite or combined probability. Composite probability. So composite probability means the system has the energy E and E dash in two parts, and this will be the product of the two, because two are independent, therefore it is the product of the two. So C dash, and then omega E, and then omega E dash. So this is the composite probability. Now if we want that this probability has a most probable state, so for maximum probability means the state of equilibrium. Most of the time the system wants to remain in the state of equilibrium, and therefore the maximum probability or the most probable state is the state of equilibrium. So for maximum probability, the first derivative of this composite probability must be 0. So the condition is that day by P having E dash divided by deba E, that should be 0. And before taking the differentiation, we will take first the log of the two, of both side. So taking the log of the both side, so ln P E dash is equal to log of C plus log of C dash plus log of omega E and then log of omega E dash, and then take the differentiation of both side and put the differentiation is equal to 0. So deba E of ln P E dash is equal to, and this is equal to 0. This is equal to 0. So what will be the differentiation of ln log constant log C? This will be 0 because this is a constant term, so differentiation is 0. So 0, and the differentiation of the log C dash is also 0. Now the differentiation of this. So this differentiation is 1 upon omega E. 1 upon omega E into dE. 1 upon omega E into dE. Into dE. And for the other, because we are differentiating with respect to E, so here in the second term there will be one more term, one more factor, 1 upon omega E dash and then deba E dash by deba E, and this is equal to 0. This is equal to 0. So what we get? We get the condition that 1 upon omega E into deba E plus 1 upon omega E dash into deba E dash by deba E, this is equal to 0. And because deba E dash upon deba E is equal to minus 1, this is equal to minus 1, therefore we have the condition that 1 upon omega E deba E is equal to minus deba E dash upon omega E dash. It means that if the two systems are in thermal contact with the energy E and E dash, there will be no minus here because on the other side it will become plus. So the property or the factor given by 1 upon omega E deba E remains constant. So 1 upon omega E deba E, and here it is 1 upon omega E dash deba E dash. If we have three systems, then this will be also equal to 1 upon omega E double dash deba E double dash. So this property is a constant property. Now go to new page. So if the two systems are in thermal contact, if two systems are in thermal contact with each other, then the property deba E upon deba omega E, this property is constant. And this term can also be written in a different way. I have written the derivative, but if we write it in terms of the differentiation, then it will be deba E into log of omega E. So this is also constant. This value can be also, this value is the result of this calculation, and therefore we can also write it as deba E of log omega E is equal to constant, and which is also equal to deba E dash into log of omega E dash, which is constant. So this property is defined as a beta property. This is called beta. So beta value is defined as deba E omega E. This is the beta value, and for this will become beta dash, this will be beta dash, this will be beta dash, and this is equal to beta. So beta is a property such that when two systems are in thermal contact, then beta is equal to beta dash. So this is the condition for the equilibrium when the system are in thermal contact. Thermal contact. If two systems are in thermal contact, then the condition of equilibrium is defined by beta is equal to beta dash, where beta is given by this expression and beta dash is given by this expression. Now we have a prior knowledge that when two systems are in thermal contact, then in equilibrium we know that temperature is equal. T1 is equal to T1 is equal to T2. This we already know that when two systems are in thermal contact, then in equilibrium the temperature of both the systems will be equal, because if the temperature is, if there is a difference in the temperature, then heat will flow accordingly up to the time when temperature becomes equal. So in thermal contact at equilibrium, temperature is equal, and here we are saying that in equilibrium a property known as the beta property is equal to each other, means beta is equal to beta dash, and here we have T is equal to T dash. It means that there should be some relation between beta and T. So let us investigate what is that relation between beta and T. So that relation we can derive here, because beta is given by deba E omega E, and omega is E is the number of the microstates. So it has no unit, it is unitless. Number of microstates means it is a number, so no unit. And then in the denominator we have energy term. It means that beta is inversely proportional to 1 upon energy. It is inversely proportional to 1 upon energy unit. 1 upon energy unit. And temperature, you know that temperature is directly proportional to the energy unit. Because temperature is the measure of the kinetic energy. So larger be the kinetic energy of the particles, the more will be the temperature. So temperature is directly proportional to the energy unit, and here beta is inversely proportional to the energy unit. It means that there is inverse relation between beta and T. So we will write 1 by beta is proportional to temperature, or to change the proportionality into equality, we will multiply it by some constant kt, and this some constant k is the Boltzmann constant. This is the Boltzmann constant. So now we have an important relation that 1 by beta is equal to kt, and this is very important relation. And in our further expression we will use often beta instead of the kt. So instead of kt we will use 1 upon beta. So now we have to remember this relation, 1 by beta is equal to kt. Now go to the last topic, which is a very small topic. And put the heading relation between entropy and thermodynamic probability. Relation between entropy and thermodynamic probability. Thermodynamic probability. If you get a question that derive the relation between entropy and probability, then again you have to do the same thing. Sometimes we don't write thermodynamic word and simply we write relation between entropy and probability, or relation between entropy and thermodynamic probability. Both are the same thing. So now we know that at equilibrium, at equilibrium, the thermodynamic probability will be maximum, or let us simply write probability will be maximum. Probability is maximum. The equilibrium condition is the most probable state, and therefore at equilibrium the probability is maximum. So this part is from the thermodynamic, or from the statistical mechanics, and thermodynamically we know that at equilibrium, thermodynamically we know that at equilibrium the entropy is maximum. Entropy is maximum. At equilibrium, entropy is maximum. So at equilibrium we have two different conditions. One is that the probability is maximum, and that is that entropy is maximum. It means that there should be some relation between probability and entropy, and we have to derive that relation between probability and entropy. Now using the second law of thermodynamics, second law of thermodynamics, we have a relation between the entropy, temperature and energy, and that relation is d by s d by e is equal to 1 upon t. So we have this relation d by s d by e is equal to 1 by t. So now we have to manipulate this relation, and by manipulating this relation we will get the relation between entropy and the thermodynamic probability. So now we can write it as d by s is equal to d by e upon t, d by e upon t, and then we have relation that beta is equal to 1 upon kt, or kt is equal to 1 by beta. And what is beta? Beta is equal to d by e of ln omega. Beta is equal to d by e ln omega. So first we will replace this t. So 1 upon t means k into beta. Using this relation, 1 upon t means k into beta. So let us write it here, k into beta into d by e, and then substitute the value of beta. So beta is equal to d by e into ln omega into d by e. So we can cancel this d by e, and we are left with k d by ln omega, k d by ln omega, and this is equal to d by s, and therefore we write it as d by, because k is constant, so we can take inside the differentiation. So it will be d by k ln omega, and this is d by s. So now this reflects that s is equal to k ln omega. So this is the relation. This is the relation that entropy is given by k ln omega, where omega is the number of microstates. Omega is the number of microstates. Number of microstates. Now you must have heard, or you might have studied somewhere in thermodynamics, that entropy is the measure of the disorder. Entropy is the measure of disorder. Is the measure of disorder. Disorder. Disorder means larger be the disorder, more will be the entropy. So our universe is moving towards disorder. Our universe is moving towards disorder because at the time of Big Bang there was order. All the materials were concentrated into one place, but universe is expanding and therefore it is moving towards the disorder, and therefore the entropy of the universe is increasing. Entropy of the universe is increasing. Universe is increasing. Entropy is increasing. Now we can prove this statement that entropy is the measure of disorder using this relation S is equal to k ln omega, because omega is the number of microstates. So more will be the disorder, more will be the number of microstates, and if we have perfect order, then number of microstate will be 1. If we have a perfect order, then for perfect order, ordered system, for perfect ordered system, perfect ordered system, the number of microstate will be 1. So if the number of microstate is 1, then what will be the value of entropy? ln 1, log of 1. Log of 1 is 0. So it means S will be 0. It means that S will be 0. So this relation also verify this statement that entropy is the measure of disorder, and when there is perfect ordering in the system, then the number of microstates will be 1 and then entropy will be 0. So at the perfect ordering, the entropy is 0, and then the system moves towards the disorder and the entropy of the system increases. So this is all about this topic. Now if you have any query or any doubt about this topic or about the today's lecture, then you can ask.